Good day. I'm Rosalind. Welcome to today's presentation on risk management. Risk management, this is a super important topic in security. How do we best protect the assets across an entire organization? We never have unlimited budget or an unlimited amount of time available to perfectly protect everything. So, how do we best protect the assets within the organization, given our limited budgets and time? One super useful method to help us to figure this out is risk management. Risk management is an essential component of any comprehensive security program, as it enables organizations to prioritize their security efforts and allocate resources effectively. Risk management is fundamentally focused on the identification, assessment, and prioritization of risk, and the economic application of resources to minimize monitoring and control. To better understand this, let's look the annualized rate of occurrence. ARO is an estimate of the probability that this event will occur over the course of a year. The single loss expectancy, SLE, is the estimated loss that would be incurred if the event happens. Annualized loss expectancy, ALE, is the estimated loss from this risk over the course of a year. The following equation is used to calculate the annual loss expectancy. For example, if an undesirable event has a 1% probability of occurring over the course of a year, ARO, and the consequences of that event occurring would cost $1,000, SLE, then the annualized loss expectancy, ALE, can be calculated as 0.011, $1,000, 4,10,000. The risk for this event would be considered greater than that of an event that has a 10% probability of occurring, at a cost of $50,000 per occurrence. 0.10 of $50,000, 1 at 4 of $5,000. There are several strategies for addressing risks. Acceptance. When the cost of avoiding a risk outweighs the potential loss of a risk, an organization will likely accept the risk. For example, spending $1 million to avoid a risk that might cost the organization $1,000 per year clearly doesn't make sense. A decision to accept a risk can be extremely difficult and controversial when dealing with safety-critical systems because making that determination involves forming personal judgments about the value of human life, assessing potential liability in case of an accident, evaluating the potential impact on the surrounding natural environment, and estimating the system's costs and benefits. Avoidance. An organization may choose to eliminate the vulnerability that gives rise to a particular risk in order to avoid the risk altogether. This is the most effective solution, but often not possible due to organizational requirements and factors beyond an organization's control. Mitigation. Reducing either the likelihood or the impact of the occurrence of a risk. This can include approaches like N-version programming or redundancy, transference. A common way to accomplish risk transference is for an individual or an organization to purchase insurance, such as auto or business liability insurance. Another way to transfer risk is to outsource the risk by contracting with a third party to manage the risk.
Manufacturers of safety-critical systems must sometimes decide whether to recall a product when data indicate a problem. For example, automobile manufacturers have been known to weigh the cost of potential lawsuits against that of a recall. Manufacturers of medical equipment and airplanes have sometimes made similar decisions.
Reliability is a measure of the rate of failure in a system that would render it unusable over its expected lifetime. For example, if a component has a reliability of 99.9%, it has a 1 in 1,000 chance of failing over its lifetime. Although this chance of failure may seem low, remember that most systems are made up of many components. As you add more components, the system becomes more complex, and the chance of failure increases. For example, assume that you are building a complex system made up of 7 components, each with 99% reliability. If none of the components has redundancy built in, the system has a 93.8%, 97 probability of operating successfully with no component malfunctions over its lifetime. If you build the same type of system using 10 components, each with 99% reliability, the overall probability of operating without an individual component failure falls to 90%. Thus, building redundancy into systems that are both complex and safety critical is imperative. System engineers sometimes refer to a system with 5 nines, 99.99999% reliability. This translates to a system that would have only 5.4 minutes of total downtime in a year. One of the most important and challenging areas of safety-critical system design is the system-human interface. Human behavior is not nearly as predictable as the performance of hardware and software components in a complex system. The system designer must consider what human operators might do to make a system work less safely or effectively. The challenge is to design a system that works as it should and leaves little room for erroneous judgment on the part of the operator. For instance, a self-medicating pain relief system must allow a patient to press a button to receive more pain reliever, but must also regulate itself to prevent an overdose. Additional risk can be introduced if a designer does not anticipate the information an operator needs and how the operator will react under the daily pressures of actual operation, especially in a crisis. Some people keep their wits about them and perform admirably in an emergency, but others may panic and make a bad situation worse.
Poor design of a system interface can greatly increase risk, sometimes with tragic consequences. For example, in July 1988, the guided missile cruiser USS Vincennes mistook an Iranian air commercial flight for an enemy F-14 jet fighter and shot the airliner down over international waters in the Persian Gulf. 290 people on board were killed. Some investigators blame the tragedy on a lack of training and experience on the part of the operators and the confusing interface of the $500 million Aegis radar and weapons control system. The Aegis radar on the Vincennes locked onto an Airbus 300, but it was misidentified as a much smaller F-14 by its human operators. The Aegis operators also misinterpreted the system signals and thought that the target was descending, even though the Airbus was actually climbing. A third human error was made in determining the target altitude. It was off by 4,000 feet. As a result of this combination of human errors, the Vincennes crew thought the ship was under attack and shot down the plane. In conclusion, effective risk management is essential for mitigating potential losses and ensuring the success and safety of projects and systems. By understanding the various strategies and considerations involved, organizations can navigate the complex landscape of risks more adeptly. Thank you for joining me today. Remember, when it comes to risk management, knowledge is power. Stay vigilant, stay informed, and stay safe.